And first I want to actually congratulate all of you survived the first day. And also to myself, because I didn't lose my voice, so I still can talk today. So I'm okay to talk now, okay. Also, I was asked a question yesterday, asked me about the advantage and the disadvantage of ODEs versus agent-based model. It's actually not fair to talk about this now because we haven't really teach the ODE modeling and agent-based modeling yet. However, make it simple. When you start to learn the modeling, you will feel like that the agent-based modeling will be much easier to actually get your hands on, because agent-based model itself is rule-based. Okay. So you actually don't need to write down equations for agent-based model. Okay. So what you need to do is specify the rules, which means I want A and B to react and generate C under some condition. That's all. And to do ODE modeling, you have to learn the language. I actually spent 3 hours, okay, yesterday. You have to grasp that kind of language. You have to know what's derivative and how you construct the right-hand side. That's actually what we're going to talk about today, okay. However, after a while, you will find out that agent-based modeling is pretty good for simulation. However, if you want to do any inference, okay, any inference or parameter estimation, you cannot find any actually tool to do that right now. I'm developing something, but that only works for a small system. If you have a system, usually if you have agent-based model, you probably will have thousands of factors in the system. There's nothing right now actually for dealing with this kind of high-dimensional thing. For small system, you have like 10 to 20 factors. I have something that can work for this kind of thing, but not really for this kind of high-dimensional thing. ODE is on the opposite. Actually, you have many available methods for inference, for sensitivity analysis, for identifiability analysis. So that's actually something we're going to cover today. So I'm not saying ODE is better than agent-based model or agent-based model is better than ODE. If you check my homepage, actually I have packages, computing packages for both. Okay, both ODE and agent-based models. So use them as you need it. Okay. So now let's back to the ODE, and this is gonna be the whole day lecture. Okay. So inhale first. What? My homepage? Oh, you can Google my name. The first link should be my homepage. Okay. Okay, let's start. So I will start with this question, okay? Why should we care? Dynamics. Care about dynamics. So I'm going to talk about a real example, actually, that just happened like 2 months ago, okay? When I was visiting another university, and I was actually asked this question. They actually designed experiments. They want to look at the gene expression level data, okay? And they collect the data at day 0, 3, and 6. What they do is that they first identify the significantly expressed genes at day 3 by comparing the data with the baseline data at day 0. That makes sense, right? And what they do is they again determine the significantly expressed genes at day 6 by again comparing with the baseline data at day 0. So now the next thing they do is that they want to find out what's the overlap between day 6 and day 3. And surprisingly, they just found out 2 and 3 significant genes, they overlap. So what's the problem there? Let's suppose there should be hundreds of genes, okay? Right? You will not say, okay, only 2 or 3 genes are involved in one, biological process. That sounds weird, okay? Usually it's not the case. So what they expect is they can find hundreds of genes, but they only can find 2 or 3 genes overlap between the set A and the set B. That's what I defined. So they ask the question whether they design the experiments wrong, or they collect data wrong, or they just lack of understanding of the nature of the system. So if we look at the gene expression data, it's not their data, okay? It's just data I grabbed from a bioinformatics journal paper. If you look at the gene expression pattern, it's not static. It's dynamic. It has up and down. And some of them have just one mode. But the others have actually more than one mode. So the question here, if the system is dynamic, I cannot just randomly pick 2 time points. That will not reflect the true, the true pattern of the process. If I picked it wrong, for example, if I picked here, I happen to capture this peak. However, this is actually day 60. For this gene, day 60 is just the linear. If you just get a snapshot here, you probably will see this gene is not doing anything. But actually, it's misleading. If you look at day 20 or day 80, you actually see 2 prominent peaks there. So that's why for dynamic system, it's actually misleading to just use the 2 time points, get a snapshot, and do a comparison. Also, another message I want to deliver is that if you are doing this kind of gene regulatory network or metabolic network, my suggestion will be try to use a dynamic system and collect frequent time course data. That will give you the answer you want. Otherwise, you will get something surprise you. So now we know that it's important to use dynamics. If the system itself is dynamic. If for us, since we're talking about how to use modeling in immunological research, immune system itself actually is changing, over time. For example, the development of memory, immunity, or the effect of aging, your immune system is changed versus time. Also, even within a short time window, for example, within 2 weeks after the influenza infection, your immune response also changed. For example, if you measure the concentration of the antigen-specific antibodies, or you measure the number of immune cells, or you measure the number of the gene expression levels, they actually are dynamic. You see a dynamic pattern in the data. Static model and method cannot actually be used to analyze dynamic system. That's for sure, unless you are interested in the steady state of the dynamic system. Steady state of dynamic system is not dynamic anymore. It's actually static. So thinking in dynamics actually will change the way we design experiments, also the way we develop method. So not by just doing 2 time point simple 2-group t-test. Now you cannot just use the 2-group t-test to compare this kind of thing. If you use a dynamic model to describe the data, and then based on the model do the test, that'll give you the reliable answer. So now let's back to the question of why use ODE. Although we have talked about ODE a lot, But here is actually the justification I can find, okay, or at least I believe, okay. So there are actually a large number of processes are spatially homogeneous, okay. Like PD I mentioned yesterday, it's a little bit difficult to understand, but another problem is PD, you probably will not find that many, okay, application problems for, as you can find for the ODE, okay. Also, ODE is actually, they are widely accepted, okay, in many disciplines, mathematics, engineering. Okay, now we're doing biomedical research. We also use ODE. And there are three good things about ODE is that it's easy to use ODE to capture the essential behavior of dynamic systems. For example, the nonlinearity or delay we just talked about yesterday. And ODE, you can use it it's easy to use ODE to interpret parameters. For example, the doubling time and the half-life. That's two examples, okay, we mentioned yesterday. And also it's used to use ODE to do predictions, okay. Now, there's another reason to use ODE is that there are many available methods, okay, if you want to do a model-based analysis. I list some of them, okay, identifiability, bifurcation, sensitivity, robustness, parameter estimation, model validation, and selection. So if you use model a lot, you will get a chance to use all these techniques, okay, actually. And but for today, we just talk about the necessary, okay, techniques due to limited by time. Now I want to remind you again what's the basic, okay, structure of ODE. We have independent variable, dependent variable, parameter, time window, and the initial condition. Okay, that's it. So now let's start to actually do some modeling. Okay, yesterday we talked about the general, okay, concept and the computing method. But we haven't talked about how to actually construct models that can describe your biological problem, okay? Let's start with this very simple example. So consider consider the case that we have 164 positive T cells in culture, and assume these cells produce 10 daughter cells per hour. But we make assumption that daughter cells will not produce more cells. That's not reasonable, but this is just for simplification, okay? And how we model this one? So today you get handouts and you really need it because you need to take lots of notes, okay? And I'm gonna use the board. So we let xt denote the number of cells, okay, at time t. That's a notation. So now actually I'm gonna use this technique, okay, again and again to construct the model. So remember yesterday I mentioned that the basic idea of ODE modeling is that we look at the change within a short time interval. Okay, so this is what I'm doing. Okay, I'm looking at the change of anything. Okay, of the variable during a small time interval. So here, this is a difference. Okay, in the cell number after delta t. Okay, so what's the right hand side? We have we know that the rate, okay, is at 10 daughter cells per 100 cells per unit time. Right? It's giving, okay. each 100 cells can produce 10 daughter cells per hour. Okay, so at time t, how many 100 cells we have? That will be this, right? So this is how many 100 cells we have at time t, xt divided by 100. Then we know each 100 cells produce 10 daughter cells. We multiply by 10, right? And this is 10 cells per hour. But right now we're talking about delta t. So we also need to multiply delta t. Does that make sense? Okay. So that will be our very first model. Okay. Easy. Question? No. Good. So what I'm going to do next is move or divide delta t at both sides. Then I get what? The change divided by the time interval. And this we cancel out. We get 0.1. And what's this? This is a rate change per unit time. So I can just write it as x dot. Oh, sorry. Probably I should write here. So our first ODE model is derived. Simple or yeah, it is simple. So far, right? So again, I want to remind you the way how we derive this kind of thing. We consider the change in a variable after a short time interval. So I will always start with this one, okay? T plus delta t minus xt, okay? And this change depends on what? That depends on what information you know, okay? Then you multiply, this is the rate, then you multiply the time interval. Then you divide the delta t on both sides. Then you just get the ODE model, okay? That's how we construct the ODE models. I'm gonna always use this technique through the, all the, 3 hours lecture. So that's a basic idea. Now, let's look at this one, okay? Oh, I think I made some mistake here. It's actually a little bit complicated than what I want to talk about. Now we made assumption that the daughter cells will not produce new cells. So I should not put xt here. Okay. So our model actually will be okay. That's right. No. No. Yep. Okay. So now we made the assumption that the daughter cells will not produce new cells. So it should be always the original 100 cells produce 10 cells per hour. Okay, so that's why we should only have this one. Okay, what I just talked about actually is the next model. Okay, so let's just make this unreasonable assumption. Okay, 100 cells at the beginning, and they produce 10 cells per hour. So that's 10 cells per unit time per hour. Then you multiply the time interval. For example, if the time interval is half an hour, then you can only produce 5 cells, right? Not 10 cells. So again, we still divide delta t at both sides, and you get actually this simpler equation. Okay, x dot is equal to 10. So what's the solution of this one? You don't need a numeric solution. Okay, this one actually has a analytic solution. X t should be equal to, what's the initial number of cells? Plus what? 10 multiplied time, right? This is your solution. So if you draw the result, you should have a straight line. Start with 100, right? It's t, xt. So this one is called, the reason actually I want to mention this model is because it has a name, okay? It's called a linear growth model. Yesterday we talked about the exponential growth model. That's actually the next model I'm going to talk about. Okay, this is called a linear growth model. And now we're clear that if I have a linear growth model, we made assumption that the daughter cells will not proliferate or divide anymore. So if you engineer the cells, okay, you can do that. Okay, but usually you probably don't want to. Okay, so now let's talk about the assumption. Okay, if we think the assumption that the daughter cells will not produce more cells is not true, okay, then we want to have the division of daughter cells back into the model. Now we saying that each 100 cells can produce 10 cells per hour. So it doesn't matter they are the original cells or they are the daughter cells, okay? Then what we're gonna do is what I just did actually. So now I'm gonna do this, okay? Because it doesn't matter they are daughter cells or original cells. At time t, they all can divide. So now I calculate how many 100 cells I have, okay, and multiply 10 cells, and then the time interval. Okay, so now here you will have 0.1 xt. And now this one will change to 0.1 xt. So this one also has a closed form solution, right? We start from 100 cells, right? And it's an exponential growth model. So it should be (0.1 multiply t). If t is to 0, then we know E0 equals to 1. The 1 multiply 100 is still 100. So you still start from 100. But now if you plot the result, it will be exponentially growth. Okay. So that's the so-called exponential growth model. Okay. How I get that from here? You need a little bit math, so to do that. So, okay, let's try. Okay. dx dt is equal to 0.1 x. That's what we get, right? And the next thing I'm gonna do actually is move x here. Right? Divide x at both sides. Okay, that makes sense? Now, this one actually can go to the denominator. It's actually log x dt. Okay, this one holds because just because d log x is equal to this is a sort of a mathematical equation. Okay, you need to use to derive the exponential. But if you don't know how to get there, it's fine. Okay. So this is a key step. I don't want to distract you from the modeling side. This is just more like a mathematics. Okay. So then from here, you see, I can have d log x dt, right? And now, yeah, integration. You do integration. Yeah. So this integration is equal to from the initial condition to the current time, okay, it's t0 to t1 to t, okay. Here is also t0 to t. So this side you got 0.t because we let t0 equals to 0, okay. Then the right-hand side you get 0.1 multiplied t. Then you have this one. So that's how you actually derive this kind of thing, because this one minus this one actually is equal to two log numbers subtract actually is equal to the log of the ratio. Okay. Then you have 0.1 t. And now you take exponential at both sides. And this cancelled. You get x equal to x0 multiplied e 0.1 t. Okay, that's how we get there. So this because this one is very simple, you can actually derive the closed form solution in this way. But for a little bit more complicated equation, I'm not sure anybody can do that. Okay, so that's why we use the numeric solution. Okay, a lot. So now I want to ask you a question. Okay. Now we have this model, right? And how will you interpret 0.1 here? Is that a probability? For example, can I interpret that this way? 10% of the cells divide per unit time. Is that right? How many will say yes? Don't be afraid. Okay. How many will say no? Nobody say no? Okay, one. How many will say have no idea? This actually is a tricky question, okay? When you write a paper, okay, you don't want to interpret this number as a probability. Why is that? Okay, let me do another example, okay? You all know why. So now, let's assume our rate is 200 cells per 100 cells per hour, which means each 100 cells will divide once per hour. So you get 200 cells, right? So if the cell divide fast, then I can use this rate, derive the equation again, okay? So I will start from here by looking at the change again. And how many 100 cells I have at time t? That's this one, right? And we know each 100 cells will produce 200 cells per hour. When you multiply 200, then I multiply the time interval. Same as here, right? Now, what I will get? I divide delta t at both sides. I get is that right? So if this coefficient is a probability, it cannot be greater than 1. Okay? Probability can be only between 0 and 1. So this is not a probability, okay? You cannot interpret this as 10% of cells divide per unit time. It's not that way, okay? This is just a rate, okay? So this number is greater than 0 and can be any positive number, okay? So it's not 10%. You cannot interpret that way. That would be wrong, okay? So this is just a rate, okay? How fast the cell can divide per unit time. So now let's look at these two questions, okay? So under the new assumption, okay, how many cells we have after 1 hour for the exponential growth model, okay? How many cells we have after 1 hour? Should it be equal to 110 or greater? It's not really a tricky question, okay? Just do some calculation, okay? We can get the answer. So we know the analytic solution is this one, right? The exponential growth model. After 1 hour, what's the number? Much like 1. Okay. Actually, what you will get is let me see. 110.52. So you have half cells here. So that's why when you use ODE, okay, you are modeling the mean. You will get a real number, okay. And for now, it's slightly greater than 110. Okay, that's reasonable because the exponential growth model should actually go faster, than the linear model. So, and actually, the point here I want to address is just this part. Okay, you use ODE model, you will get a half cell, okay, or like that, okay, because you are modeling the mean. And now let's look at question 2. So again, in the exponential growth model, yeah, that's what I just talked about. And again, I want to make sure that you don't write 10% of cells is dividing per unit time in your paper, okay? That's it. And now, let's make it more realistic. So we consider the growth model, okay? We haven't considered any death in the model. It's not reasonable because that depends on the time window, okay? If it's a short time window, probably you're okay. But if you're talking about 1 week or 2 weeks, okay, there will be some, cell deaths. So again, we start with 100 CD4 T cells in culture. And the progenitor and the daughter cells can proliferate or die. Okay, so they both can have the, the two types of behavior, proliferation or death. So assume that, again, we assume that each 100 cells will produce 10 daughter cells per hour. However, 5 out of 100 cells will also die per hour. Okay, that makes sense? So how we do this modeling? The growth rate? The growth rate is here, right? This is the growth rate. This is the death rate. This is the death rate. Okay. 5 out of 100 cells will die per unit time, per hour. This is the proliferation, okay? So how we do this? We know how to do now we know how to model the growth, right? Now we add the death into the model. So let's write it down, actually. The growth rate is 10 cells like before, okay, per 100 cells per unit time. Now the death rate is 5 cells per 100 cells per unit time. Now, once we have these two, the rest is just the same, okay? X t plus delta t minus what? xt, right? And it's equal to what? Now we have growth, have death. So let's first consider the growth. Growth is exactly the same as before, right? Yeah, should be the same as before. So we calculate how many 100 cells we have at time t. And then these cells will produce 10 cells, okay? Per 100 cells will produce 10 cells, okay, per unit time. And then we multiply the time interval. That's just as before. And the only new thing here is that we need to consider the deaths. So we subtract the deaths. Again, because 5 out of 100 cells will die, first I calculate how many 100 cells I have. Okay? Then they will die. This is per unit time. I still need to multiply delta t.
So you want to have 100 over 100 when you actually put the numbers into
what?
this? You need to have 100 over 100 when you actually put the numbers?
No.
You're just doing it, okay.
Because here, I already used this information.
Oh,
See,
okay.
by divide by 100, right? Yeah. So this is a growth, this is death. Okay. So actually, these two terms, they are constructed in a similar way. I just put a different sign, okay, in front of the second term because it's death. Okay. So if you compare these two terms, you will notice that they are constructed in a very similar way. Okay, just a sign difference. So what's the next thing we're going to do? We divide delta t at both sides. Okay, that's all. After that, you will get 0.1 x minus 0.05 x. Right? Mm-hmm. So eventually, I will get that. So this is called growth rate. This is called the death rate. And after I subtract the death rate from the growth rate, this one is actually called net growth rate. Okay, it has a name. Okay, it's called a net growth rate. Okay, so any questions so far? So we're doing okay? Okay, so I try to write. Okay, okay, good. So what I wrote down here is the last line is xt. That's the final model. Okay, and this one is called net growth rate. Okay, because it's growth rate subtract the death rate. No, it's still exponential because you have x here. Okay. Yeah. If it's linear, then you have just a constant here. Okay. That would be different, right? So now this slide actually is the terminology, okay? Just for convenience, okay? In case you forgot the name, I just give them, okay? You only, it doesn't matter actually, the symbol, okay? I personally use the rho to denote the proliferation rate, delta to denote the death rate, and the difference between rho and delta is what we call the net growth rate. So let's think about, okay, what is the problem of this model? This problem is not about the model structure, okay? This problem is more about the parameters, okay? So here's one. If we do not know the values of both rho and delta, can we actually determine them from data?
Rate can be calculated. If you know the number of cells per hour.
Yep. Let's do this, okay? That's actually a very interesting question, okay? Why it's interesting? Because look at, let's say, here's my data. Okay, looks like an exponential growth model, right? I probably can fit a model like this. Okay, and that's the model we have. And now I have two parameters, rho and delta. I don't know both of them.
Yeah, you can actually do it.
Can I determine both of them?
No, you can do it.
No. Yeah, that's a good answer, because you only need one. You can only determine the difference from the data. That's rho minus delta. Okay, you cannot determine rho and delta separately. Okay. The reason is that rho and delta always stay together. Okay, they stay together. So you can treat the difference as one parameter. So in your data, you can only determine one parameter from the data. So you will not be able to tell what's the exact value of this one or what is the exact value of this one. You can only tell the difference. Does that make sense?
Unless you create an experiment that measures the newborns or the...
That's case 2. So case 2, if we know one of the parameter values, then actually I have data. I can determine the left one, right? I know this one, I can determine this one, or I know this one, I can determine this one. So basically, you can interpret it in this way. If I have two unknown variables, I need two equations to determine the value. If I only have one equation, but I have two unknown variables, then you have an infinite number of solutions. Okay, that's sort of the problem associated with the model structure. Okay, so actually we will actually be back to this question again. This one is actually the very simple example of identifiability. Okay, this is what we call identifiability. So which means we want to answer a question whether all the model parameters can be uniquely determined from data with a given model structure. Okay, so here is the that's the keyword. Okay, so we have talked about the exponential growth model. However, there are some variation of this model. You can also write a model like this too. Okay, the first one, you have a constant growth rate, but you have an exponential death. The second one, you have exponential growth, but you have a linear death or constant death. Okay, I'm not saying which one is better or which one must perform better. Actually, it depends on your assumption. Okay, if you have evidence to show that the growth is a constant rate or the death is a constant rate, then you go ahead with the model structure. Okay, if you don't have any justification, okay, you only go with the exponential growth or death will be a option. So now we talked about the growth, we talked about the death. Let's make it more interesting. How about we have a limit to growth? So we know that the environment, okay, have limited resources. We don't have infinite resources, so the cells can keep growing. Okay, if it has a limit of the resources, then when the cell number reaches a certain threshold, it will stop growing and stay there, right? And the pattern you will expect to see is not this exponential curve anymore. It should be some curve looks like growth first, then saturate, and you get a plateau, right?
Lag phase. It's called lag phase.
Yeah, or called a steady state. So there are different names for that. So how we model this? So now you're seeing what I'm trying to do, right? I'm adding one block by one block, okay? So eventually you will have a realistic model. So to model your, culture, whatever, okay, cell growth culture. So how we do this? Okay, let's start from this model, okay? It doesn't matter actually which model you choose, okay? You can also choose this model, okay? That depends on your assumption, okay? So let's say, okay, if I have a model that considers the growth and death, and the death is a constant, okay, death rate is constant. So we know that the cell, if we have a limit of resources, okay, limited resources, then the cell will grow slower if the number of cells increase, right? That makes sense? Of course, because the resources are limited. And the second thing we know is that if the number of cells is equal to the maximum number of cells allowable, okay, then cells will stop growing. Then this rate should become 0, right? If x. Okay, so we're trying to actually develop a structure for the parameter rho such that it satisfies this condition, right? So what we need to do actually is introduce this model structure, okay? So we let rho to be a function of variable and other parameters. So now, if my x is equal to x max, the ratio becomes 1. 1 minus 1, you get 0. So now rho will become 0. And at the beginning, what's the ratio at the beginning? Right? The initial number divided by the maximum number. Okay, let's write it there. Okay. So rho T0 is equal to gamma minus x T0 divided by so if at the beginning this number is small, then the ratio will be small. And 1 minus the small number is almost 1. And the multiply gamma is approximately equal to gamma. So if I plot, okay, my rho, it will be, if I plot rho versus x, okay, it will be a straight line with a negative slope. Okay, here rho equals to 0 and x should be equals to max, right? And it cannot be greater than x max. And here is approximately gamma. Okay, so here is 0. So now this, okay, I see.
On the growth curve, what determines when you get the inflection?
Mm-hmm.
I was wondering, like, biologically, what determines when you get inflection?
If I plug in this one into here, you will have right, and you can solve this equation. This one will tell you, okay, what's the time? Okay, you need it to reach the maximum. And I don't have an analytical solution right now, but I think that this one should have a closed form solution. Okay, because it's actually also a simple, Actually, I can do it, but don't waste the time now. Okay, so that will be, if you are interested, okay, in this one, okay, what's the time you need to reach the maximum? Okay, solve this equation. That I can tell you actually. So I give you this example just because I want to show that sometimes, okay, some mod parameters can be a function of other variables or parameters. Okay, they are not just always, a constant. Okay, they can be a function of other things. So now we add the limit to growth in the model. So anything else you want to add to this model? We have this, we have proliferation, we have limit to growth. So what else you want to add? Not that much, right? Okay, then we are done with this first model, okay? So it served its purpose, right? And the next thing actually I want to move on to is a more realistic, problem. So how we model the cell infection, okay, caused by virus. And I put a subtype there. It's a single compartment model. Single compartment or multiple compartment. Actually, later we're going to have a multiple compartment model. But for single compartment model, let's just assume that we have a room, okay, and we have many particles of different species. And these particles, they can interact with each other within this room. And this room, because we only have one room, so we call it a single compartment. Okay. If multiple compartment, which means, for example, I have this is lung, this is my lymph node. Okay. This is biologically there are two different organs. Okay. So we can treat them as two compartments. And also, again, here you can have a number of particles of different species. For example, dendritic cells, T cells here, B cells here, or same thing here. You have virus, you have T cells, you have B cells, something. Okay. So that's the definition of single compartment and multi-compartment model. So now we want to model the cell infection by virus. So we need to actually, the first unit when we construct a model, okay, we need to specify the behavior, okay, of all the players in this game. So what players we have in this game? Of course, we need to have cells, right? We need to have virus, okay? So the infection can happen. Otherwise, you will not have, if you don't have cells infected, then it doesn't matter, okay? The modeling. So we can let V denote the number of viral particles, okay? That's our first player in the game. And we can let T denote the number of targeted cells. So now let's consider the possible behavior, okay? First, the virus can be regenerated, right, by infected cells. So let's assume that there's a exponential growth of virus. Now we're familiar with this term, right? It's exponential growth of the virus. So secondly, we have a loss of random particles, okay? Or let's just say V, okay? Due to infection. Why is that? Because if a virus needs to infect a cell, it needs to go into, first need to bind to the cell surface, okay? Then go inside, right? Then you will see less viral particles in the lumina, okay, or in the environment. So there are not free viral particles anymore. And because what they're infected is a cell. They are not infected themselves. So the loss of viral particles actually depends on how many available target cells, right? But that's a good question. So that's actually what I want to talk about next, okay? So here, okay, instead of V, we have a T because the number of T actually means the chance or how easily, okay, you can get a target cell and infect. That's why this rate is proportional to T, okay? But let's put it in this way, okay? I know you have a question, okay? And actually, I will spend time later, okay, to fix it, okay? So let's say for now, okay, let's just do this, okay? So the third thing I want to do is we have considered the growth and disappearance of viral particles. Now I need to consider the growth and disappearance of T, right? So let's say let's assume that it's a linear growth. It doesn't matter actually for now, okay? You can assume a linear growth or exponential growth. It doesn't matter for now, okay? Let's say it's a linear growth for the target cell. So what will be the reason that the cell will disappear or decrease? This is a reason of growth, okay? So what's the reason of this cell will disappear or decrease in number? Because infection? Infection will turn a target cell into infected cell, right? And how about death? That's also possible, right? So now let's first consider the right? This is the loss of target cells due to infection. And for the same reason, it's proportional to V. Okay? If you have more viral particles, it will be easier for a target cell to become infected. Right? That's why you have V here. So now let's consider the death. This is the exponential death of T.
Delta V should be loss of V.
This is T because this is the death of the target cell. And the loss due to infection is already here.
It should be the loss of virus cells.
Loss of.
Loss of virus cells because it is delta V.
Uh-huh. Oh, here V is free viral particles. So the death of the target cell will not affect the number of free viral particles, right? Okay, so here is the free viral particles, okay. So now let's put them together, okay. So this is like factory, okay. You have step 1, step 2, step 3, then you just put them together, okay. So what I will do is we have a right hand side, okay, the change per unit time. So now we have the loss of T target cell due to infection. I can do this, right? And we have death of T cell. Right? We also have a growth of T cells of the target cell. That's it. So the construction of ODE model is that simple. Okay. Yes. So find out the rate, put them together. Okay, that's all. Similarly, for the V, we have the regeneration of particles. Also, we have the loss of viral particles due to infection. Okay.
I'm still not sure about that. You know, you would explain that.
Yep, exactly. So, does that make sense for now? Any question? This is going to be a good timing for a question. If not, I can answer the question of yours. So, okay. So, the question after we construct the model, the first question we're going to ask ourselves is always, does this model make sense? Okay. You have question about this term because you think this one doesn't make sense.
Yeah.
Make part of the sense, but not the really, make the full sense. Okay. So after we do the modeling, okay, we need to do model inspection. Okay, like when you build a house, okay, you need to actually do some checking. Okay, see whether the safety issue is solved, or you have enough power or whatever supply. So what's wrong with this model? If we use criterion 1, okay, every parameter and variables has units, and the units need to be consistent. Does this criterion make sense to you? Right?
Yeah, even that
You
one,
put-
term number 4 is also a little bit suspect to me.
Which one?
That's
4?
Yeah, 4.
Here, delta V. This one?
Yeah.
Okay, we go through them one by one. Okay, so first, all the parameters and variables have units, and they should be consistent. Now let's check which one is consistent or which one is not. Okay, so this one, we start from this one. This one is the loss of target cells due to infection, right? Then what's the meaning of this parameter? Should be the infection rate, right? This is a loss of target cell due to infection. This parameter has to be infection rate. So what's the unit of infection rate? The unit of delta V. That should be per unit time. Let's say hour per viral particle. Is that right? Which means how many cells one particle can infect per unit time. Does that make sense? Now, let's multiply the unit of this parameter with V. What do we get? We multiply units right now, okay? Not really the value, okay?
Oh, I see. Okay.
Just particle. Let's call it particle. Okay. Okay, so this one multiply this one, you get a per hour. What's left is per hour. Okay, because this one cancels. Okay. So you have per hour here for this term, the unit. What's the unit of this term? Cells per hour, because that's a change in cell number per unit time. So is the unit consistent? No, because you have cells in the denominator. Now you don't have anything here. Right? So what's the remedy here? I actually need to multiply t here. Why? We have more wire particles, which will make it easier to infect the cell. But also, if we have more cells, it will also make the infection easier. So it should actually, the infection should be proportional to both T and V. So by doing this, actually, model checking, okay, you find out, actually, you have a very good instinct, actually. This term has a problem, okay. You should have a T here, actually. That's the right model, okay. So another thing, okay, here. Where this one have carbon? We do the same thing, okay. We do the same thing. So this is the loss of wire particles due to infection. Okay. So how we model that? How should we model that?
It should be, I guess it should be times B in this case, probably.
You want times V here?
You go by the same idea.
Uh-huh. Or we, actually in practice, we usually just drop it. Okay. So,
But if it's not the whole factor, then you're not considering the loss of B during infection.
that's a very good question. In practice, okay, if we count a number, we should have a term in the model. However, in practice, okay, usually people don't have that term. The reason is that the number of V is usually much greater than the number of T. Okay, you know, you will have a few orders of magnitude more wire particles, you know, than the cell. So the loss of wire particles due to infection usually is neglected in the modeling because the number is too small. Okay, that's.
So then it's preferable to delete that factor since it's not important in our model, rather than adjust the units of that same factor.
This one actually is not a unit problem. Okay, this one is not a unit problem. Although we know there's something wrong with the term, but this one is not a unit problem. The main reason is that this term can be neglected. Okay, if you want to model this term, like you just mentioned, okay, I can actually, okay, make this experience, okay, like you know, make this term like this one, okay.
But if we wanted to model that one, then we would have a unit problem.
If if we just put gamma t here, you get a unit problem. Okay, that's right. So you probably will put something like this, but nobody actually doing this just because you know, the number is too small. Okay. So now let's look at this term. Does this term make sense to you? This one is not a unit problem, okay, I have to say. It is actually a biological problem, okay. We know virus cannot produce themselves, regenerate by themselves. They have to use the host cells. So the production of virus actually does not actually come from virus particle itself. It actually comes from what? Infected cells. Okay. So instead of put a rho V here, I'm gonna put a rho V multiply infected cell. Okay, that's the right biology. Okay, this is not a unit problem. It's just a biology problem. Okay. So when you write a model, you want a model that has a consistent unit, right? Second one, you can drop some negligible term. Okay, that's okay to do. Okay, if you can justify. Thirdly, you have to make the biologically correct. Okay, this is a biologically correct way. Okay, to model this. So I have started from a wrong model. Okay, and then we fix it. So that's actually the usual thing we need to do. Okay, when we do modeling. The first version, okay, of model, usually you need to modify it, even after years of experience. Okay, not just this kind of issue. There are more issues actually I'm going to talk about. Okay, probably in the third lecture, but we have. So should we stop now or? Okay, let's have a 15 minutes break. Okay.